how to make approximate programming easier through the help of types.
Yes, thank you. So I'm Brett Boston. This is some research I did with Adrian Sampson, Dan Grossman, and Luis Seze on probability type inference for flexible approximate programming. So what is approximate computing? Approximate computing is the idea that not every operation in a program has to be correct. And by operation, we mean things like arithmetic operations and loads and stores and things like that. Though for the purposes of this talk, we'll be focusing exclusively on arithmetic operations. And by correct, we mean sort of with the normal execution model you're used to on your computer. And in allowing this relaxation, it's possible to save both energy and execution time. So sort of the hardware model here is that you have a system that allows specification of every single arithmetic operator in program. But of course, actually programming this kind of system would be very difficult. So you can see in this example, if we annotate every single plus in a program, it's hard to say, for example, what the reliability of z is at the bottom, if it's a function of many of these other variables. And if you have a specific reliability you'd like to reach with z, what do you set those operators to actually achieve that? So this is not a very usable system. So we would like to allow the programmer to instead bound reliability on variables and to let the compiler do the hard part of figuring out operator correctness to achieve those reliability bounds. So we frame this problem as one of type inference and solve it using an SMT solver. So I'd like to start out by introducing a basic approximate programming language, and then I will talk about how to make that easier using type inference, and then lastly, introduce our hardware model and some of our results. So we built our system on top of NRJ, which has annotations on variables. You mark them as either approximate or precise. So you can see the first three variable declarations here are approximate. Approximation actually comes from binary operators here. So the third line has some approximation going on in that sum of A and B. The fourth line, we create a precise integer. However, precise is the default annotation, so if you leave it off, variables are precise. Assigning an approximate value to a precise variable is illegal, though the other way around is of course totally acceptable. And we allow this static endorse cast to cast approximate to precise, though this endorsement is unsound. But what if you want more than all or nothing approximation? You have a system that supports multiple degrees of approximation, and you want to work at a lower level of abstraction to take advantage of that hardware. For that, we need something a little more descriptive. So we introduced the parameterized Approx annotation. And this is sort of the crux of the research here, of the project. So this annotation takes a parameter n such that at any point in execution, the probability that the value is correct is at least n. And we define correct to mean the same as it would be during fully precise execution. And a corollary of that is that when a value is incorrect, we offer no guarantees about what that value may be. Our subtyping rules are pretty straightforward. You can assign a variable with, a value with a higher reliability to a variable with a lower reliability, but the other way around is not okay. So for example, the last line here, this assignment is illegal because A has a lower reliability than D in this scenario. Binary operators are where all of the approximation in our system actually comes from. So in this example, x and y have reliabilities of 0.9. And so what that means is that x plus y would be correct with probability of at least 0.81, given that the plus operator is fully precise. And this really just follows from the product rule from standard probability theory, which states that the probability of A and B is greater than or equal to the probability of A times the probability of B. So it's important to note then on the third line, there's no actual approximation going on here because the product of of x and y is already equal to A's reliability. However, on the fourth line, the right-hand side is a little more reliable than the left, so we have some area to some room to fudge that plus a little bit and introduce some approximation into that calculation. Some other language details is that we conservatively treat all values as independent. We don't do any sort of dependence analysis here. And control flow is only allowed on precise values. So that's the basic approximate programming language. So how can we make this easier to use? This is where type inference comes in. So if you have a complicated function you want to annotate, and while you know how precise inputs and outputs that function should be, it's unclear how to go about actually annotating the innards to achieve that. It's a very similar problem to the operator problem from the beginning. And the only way to do that with the system that I've described so far is to guess, get some errors, and repeat. But this is not a very usable programming model, so we'd actually like to use type inference here to do the hard work. So we also have a inferred approx annotation, where if you leave the probability off the approx annotation, we'll infer that probability of correctness for you. Reliability of binary operators is always implicitly inferred, such that the expression's reliability is minimized as much as possible, while still satisfying the reliability constraints from the programmer. So the idea here then is that developers use this explicit annotation where they have quality requirements. So in this example on the bottom, we care that the area of the triangle has a reliability of 0.9, but we don't really care about the reliabilities of the base and the height in that calculation, so long as they're high enough to satisfy this area constraint. So then the whole programming model looks like using these explicit annotations on inputs and outputs, and letting the innards be inferred through the use of the inferred annotation. So the very high-level view of how this process works is we take type annotations from the programmer, as well as some hardware parameters about the system they're planning on running the code on, as well as an objective function that we provide that is an abstraction over the total reliability of the program. And we pass this all into Microsoft's Z3 SMT solver. And if the system's over-constrained, we have a type error. If it's under-constrained, then we want to try to lower that objective function to try to push Z3 towards a system with a lower average reliability that is still satisfiable under the constraints provided by the programmer. So this is how this shows what the actual constraints look like that are generated on a very simple program. So if we take x and y to be inferred and then use them in the sum of, to get z, and z has an explicit annotation, there are three things to infer here. And that would be x, y, and the reliability of the operator. So you can see in the top three clumps of constraints, we've declared the operator x and y to be between 0.0 and 1.0, just because they're probabilities. Then, in the last bottom clump of constraints, we constrain z to be equal to 0.81, the programmer declared constraint. And we also know that it has to be less than or equal to the product of x, y, and operator, just from the assignment. So one naive solution to this, of course this has infinite solutions, would be to set x and y equal to 0.9 and to set the operator equal to 1.0. But this doesn't actually have any approximation in it because the operator is fully precise. So we kind of missed an opportunity to approximate where the programmer said it was OK. Z3 arbitrarily selects something that seems completely random from these constraints. But of course, the optimal result would be to set x and y equal to 1.0 and to set the operator equal to 0.81, really maximizing the amount of approximation we can do in this statement. So how do we actually push Z3 towards these less reliable solutions? Well, this is where the objective function comes in. We average all the inferred probabilities across a function of operators in the system, and we target a specific average reliability. We start with 1.0. And we can approach then an optimal result using a linear search, slowly ratcheting down that target reliability by a constant amount until the problem is unsatisfiable or times out. So here's an example of how that process looks. If we take z to be the sum of a, b, and c, we first declare our objective target to be the average of the two operators in the calculation, and then assert that that target must be less than or equal to 1.0. And we push constraints onto Z3's internal stack, slowly lowering that objective target until it's unsatisfiable at the bottom, and we can pop that last set of constraints and end up in a state that's near optimal. We also allow the use of these inferred annotations on method signatures, and if there's something to be inferred in a method signature, then we'll specialize that method at every call site, so sort of similar to C++ templates. Our analysis is totally interprocedural, so upon reaching a call site of a method that needs to be specialized, we'll jump into that method, type check it, generate constraints, and bind them to the call site. Because of this interprocedural nature, we don't allow the use of inferred annotations if there's a cycle in the call structure. So we detect that and throw an error in that case. Of course, the explicit annotations are still fine in cycles. And lastly, the programmer is allowed to bound the maximum number of times a method will be specialized. So if you don't want more than 5 versions of a method to be generated and you use it 7 times, we'll find 5 versions of that method that can satisfy all 7 invocations. So you can see an example of method specialization here, where we calculate the area of 2 different triangles, but we have a stricter quality constraint on the second triangle. So we'd like a more reliable function to be generated there. We also have dynamic types that are allowed to track the reliability at runtime for situations where we can't reason about things statically, such as summing things in a loop. And you're allowed to use this dynamic cast back to the static Approx N world using a checked endorse that takes an additional lower bound for the acceptable reliability of the value. And if the value's fallen below that reliability, we'll throw an exception. So you can see here, we have an approximate array of numbers and a running sum d, and we just sum up those numbers and then cast back to the static Approx type at the end. So that's the type inference for a system. Now I'd like to talk a bit about our hardware model. So at the end of compilation, we export operator reliabilities for every operator in the program. And then we take those reliabilities and do an instrumentation pass in the program, replacing these operators with calls to a custom function in a simulator. And this function performs the approximate operations and records some statistics about them, such as which operations were approximated and to what degree and that kind of thing. So we can get runtime statistics back at the end. We also recognize that hardware will likely not have continuous operator probability knobs. So we recognize that there will likely be some set of discrete reliabilities that are supported on any given piece of hardware. So we allow the programmer to specify these discrete levels at either compile time or runtime. And if we get them at compile time, then we can pass that information onto Z3 to get a solution that's more optimized for the hardware. Otherwise, if they're passed in at runtime, we'll just round up the inferred reliabilities, assuming a continuous model. So this is sort of how the constraints change when you pass in some number of discrete reliability levels. So you can see now, instead of binding operators to be between 0 and 1, they're bound to the discrete levels that were supplied in. So in this case, 0.9, 0.99, and 1.0. We test our system using the NRJ benchmarks and use the programming model that we expect people to use with our system, which is to constrain the inputs and outputs and to use inferred annotations on the innards. And these ranged from a few hundred lines of code to around 13,000 lines of code. Sort of the takeaway from going through this process was that there are only a few annotations needed to achieve the desired level of approximation, which for us was set at Approx 0.9. I don't have time to go through this entire table, and I'll get to these applications in a few slides. But there's all the statistics about annotations in the paper that you should check out if you're interested in that. So what this is showing is the benchmark fast Fourier transformation with 5 discrete levels of reliability on the hardware. So those 5 levels would be the bottom 4 on the legend on the right, as well as 1.0 at the top. And the y-axis here is showing the percentage of operations that were marked as being approximable and what approximation level they were actually run at. So you can see here, out of the approximable operations, we only approximated about 15 of them. That's not so great, right? There's a bunch of missed opportunity there. Things could have been approximated that weren't. However, if we take a step back and look at a varying number of supported discrete levels of approximation, now the x-axis shows the number of discrete levels supported at runtime. You can see that adding more discrete levels results in more approximation opportunities being realized. So then the question is, how big is this effect? So if we look at all of our benchmarks, now that graph from the previous slide is all the way on the left, and the x-axis now is showing the same benchmarks for various benchmarks. And sort of the takeaway here is that there do seem to be some diminishing returns after a point. So after about 5 or 6 discrete levels, it seems that adding more doesn't get you much more approximation. So this is a great thing to see because it means that perhaps there's a nice point where you can get near the continuous model on a piece of hardware without having to go and have a ridiculous number of discrete levels of approximation to get that. Also in the paper, we have full formal semantics, as well as some information on compiler warnings to aid the development process. We also have results on solving versus rounding with discrete reliability levels. So this is, once again, providing those reliability levels at runtime versus compile time. How does that affect the actual level of approximation in the system? And we also have our full system simulator and everything available online. So you should go play with it. We could use some work on modularity in our system. So because our system is totally interprocedural, we really need access to the full program when we're doing any sort of compilation. So this really means that small changes to one part of the code results in a full recompilation. We could possibly reduce this, this overhead by storing the reliability of function return values in terms of the reliability of function arguments, and some other systems do this way. We also could use some work on error messages. Right now in our system, errors in inference can only tell you that an error exists somewhere in a function, but can't tell you where. So Z3 also supports an unsatisfiable core that maybe we could use to narrow down the space that someone has to look at to figure out why their program doesn't compile. So we've built a language abstraction over flexible approximate hardware supporting multiple degrees of approximation, and we've achieved a low annotation burden leveraging type inference in our system. And we ultimately hope that this research is used to inform the hardware community. Our system allows you to write a program once and to simulate it on a bunch of different hardware configurations, right? So you can vary the number of discrete levels that the hardware supports, what those discrete levels are, and you can gather all these statistics about the actual approximation at runtime, how that compares to an optimal continuous model. Thank you.